Section 810 is called Taylor and Maclaurin series. The idea behind this lesson is to give you some alternatives to having to create Taylor and Maclaurin series from scratch every time. So when I say by scratch, I mean from the definition that you've memorized for Taylor polynomials centered at x equals c. So first I want to point out that they're using the word series here instead of polynomial, and they will be polynomials, but when they say series, they're implying an infinite series. To give you an example of, the difference, I suppose, between a polynomial of degree n, like we were doing previously, and what they're going to refer to as a Taylor or Maclaurin series. So let's say I give you f of x equals sine of x, which looks something like this. And let's say I ask you to make up a Taylor polynomial of, sorry, I'm grabbing a couple pens that are different color. So let's say I ask you to come up with a Taylor polynomial centered at 0 of degree 0 for sine of x. So, that would be this guy. Purple doesn't look much different than blue, does it? But anyway, so, and then you'd say, well, that doesn't look like sine of x at all. And I'd say, well, they agree where you asked me to center it, but then it's pretty bad. So let's say that then you're asked for maybe a Taylor polynomial of degree 1, so that would agree up to y coordinate and first derivative. Still doesn't look like sine of x, but it looks better than the degree 0. And then what if we then add in like a degree, degree 3, right? So degree 3 would agree up to the third derivative. And I don't know exactly what it would look like, but let's say it looks something like this, What if we pop up to a degree 5? A degree 5 maybe would hug the curve a little tighter. I don't know. I'm making stuff up right now. But anyway, the idea is that, if we were to go up to a degree 7, maybe it would hug the curve even tighter, So the idea is that every time you add a term to your polynomial, you get more accuracy. Well, how many terms would I need on my polynomial for it to be the sine wave? And I think we all know where we're going with this, and the answer is infinitely many. And that sounds hard, but it's not, because it's a matter of establishing a pattern and tacking on a plus ... and no big deal. So as a warm-up problem, let's say I ask you to write sine of x as a Maclaurin series. Okay, so where is a Maclaurin series centered? Centered at 0, it's my favorite thing. And so how would we go about this? So I would say, let's go ahead and make it official. F of x is sine of x. And then that's right, let's just get started on derivatives. So f prime, f double prime, f triple prime, and then the fourth derivative of f with respect to x. And by the time you do 4 on either sine or cosine, we should be able to take advantage of the cyclic nature of the derivatives. So, okay, so derivative of sine, cosine, derivative cosine, derivative of negative sine, and derivative of negative cosine. Okay, so we're back at sine of x. There we go. So we've kind of come full circle. So we know how it would go if you wanted the 5th, 6th, 7th derivative. It would just go through this cycle again. And where are we evaluating all these functions? Well, it's a Maclaurin series, so we're evaluating them at 0. Okay, so f of 0 is sine of 0. F prime would be cosine of 0. F double prime, negative sine of 0. F triple prime of 0 would be negative cosine of 0. And the fourth derivative, we're just kind of back up at the top of the list again, essentially. And that would be 0. So if somebody says, oh, well, what's the fifth derivative? Or what's the sixth derivative? You know, you could kind of take advantage of the pattern and just continue it. So, okay. So we have a good process for coming up with this polynomial. So let's go ahead and show. So we're going to go ahead and say sine of x is exactly equal to, because we're going to use an infinite number of terms. Let's see, the pre-simplified version would look like a very obedient following of the rules. Okay, and then the plus dot 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 is why we're able to say exactly here. So then look at how this sine function looks after we simplify its Maclaurin series. So you end up with x, whoops, plus, I apologize, not x squared, and not plus either. Okay, minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And then if somebody says, oh, well, guess what's next? You could take advantage of the pattern that's being established here and guess what's next. So, you know, what's going to be next? So notice the powers go 1, 3, 5. The factorials go 1 factorial, 3 factorial, 5 factorial. And then there's a pattern on your coefficients, positive, negative, positive. So what would the next term be if you had to guess? And that's what I would have guessed too. Anyway, so as soon as you can guess the next term, you definitely have established a pattern. So this lesson, believe it or not, is all about how to not need to do this from scratch process as much. And there will always be a use for that from scratch process, so you don't get to forget about it. But you do get to learn ways to not need it. And one way to not need that big, long process that we did there is to memorize the most common Maclaurin series. And I'm here to tell you that sine of x is one of the most common Maclaurin series, which is why this is your next flashcard. And it's not just your next flashcard, but it's your third to last flashcard for your collection, I'm happy to tell you. So the idea here is to memorize this, and hopefully if you notice the pattern on the exponents all being odd, the factorials all being odd, and then you do start off on a positive term, and then the signs alternate on the terms, it should be a pretty easy one to memorize. So memorize it, and I say memorize it now. Okay, so now let's talk about if you have that one memorized, you have that one in your back pocket, and you get to the AP exam, how could you use this in a meaningful way? So on the AP exam, they are likely to give you something that has this as its sort of like parent function. So let's say they gave you some mess like x to the 5th times the sine of x cubed. And they say, write the Maclaurin series for this. So let's think about your options. Option 1, let f of x equal this expression, and then do what you did up here where you start taking its derivatives. And let's think about that for a second. If this is f of x, just think for a second about f prime. Got it? Product rule, chain rule, totally doable, but it's going to be a lot to keep track of when you have to take then the second derivative and the third and the fourth. This is going to get very messy very quick, and it would be very time consuming, doable but time consuming. So let's talk about a quicker way to get the Maclaurin series for something like this. So if you go into the AP exam and you have the Maclaurin series for sine of x memorized, you could actually build the Maclaurin series for this expression up from this. And how would you do that? By simply following the order of operations. So what's the first thing that you would do to sine of x to get this expression? Well, the first thing you do is work from the inside of the function out. So the first thing you do is figure out, well, what would sine of x cubed be? So let's focus on that. We're going to build this expression up in a couple of stages. So what would sine of x cubed be? Well, what would you do to sine of x to make it be sine of x cubed? Well, you would take the x out and replace it with x cubed. And if you do that on the left side of this equation, then you could keep your equation balanced by doing the same thing on the right side. So what would that look like? It would look like instead of x, you would write, that's right, x cubed. And then here for that x, you'd substitute x cubed. For every single x, you'll just replace it with x cubed. And then you could... Anyway, and since you could simplify this. So if you did, what would you have? Actually, you know what? Let's skip simplify. I know, lovey. I'll just be a little longer, okay? Okay. Anyway, I'm going to save simplifying until later because I'm pretty sure I don't have a lot more time to talk to you. So now let's talk at you, that is. Anyway, so now let's go ahead and build this expression on the left up closer to what they had given us. So let's multiply both sides of the equation by x over 5. So let's do that. So I would have x over 5 times the sine of x cubed. And then what would that be? That would be x over 5 times, and then I think I'm going to go ahead and simplify this as I go. So x over 5 gets multiplied by the whole right side, and what would I have? I'd have x to the 9th over 3 factorial plus x to the 15th over 5 factorial minus x to the 21 over 7 factorial, etc. Okay, so a final answer could be this if you really wanted, or you could, if it bothers you to not distribute that in, you could always distribute it in as well. And so you have the polynomial expansion for x over 5 times sine of x cubed without having to do the grungy process of creating that from the definition. So what would we have? X to the 4th over 5 minus x to the 10th over 5 times 3 factorial plus x to the 16th over 5 times 5 factorial minus x to the 22nd over 5 times 7 factorial, etc. And then this would be your final answer for a problem like that. When you see this on the AP exam, what they commonly will do is they'll say, explain why the polynomial expansion for this is, and they'll give you the answer, and then you would just need to tell the story, starting with sine of x, showing your substitution, and then showing your multiplication, and then arriving at the polynomial that they gave you. So you would just kind of tell the story as to how they got there. So before we move on to the next thing, this lesson is all about really ways to avoid the from scratch process. And you can't always avoid it, but we'll show you lots of little techniques for kind of how to maneuver around it as we go. Okay, so moving on, let's say I ask you, let's do this. Let's check for a second. Let's see if you could give me the polynomial expansion for sine of x from memory. So no peeking. What is it? Do you have it memorized already? So first term, second, Third. Next one. Etc. If somebody says, oh, what's the next term? And term after that, you could always come up with it because you've noticed the pattern. And what's the pattern? All odd powers, all odd factorials. The terms alternate in sign, and you start off on a positive term. So if somebody says, well, now I want the polynomial expansion for cosine. You could, and we will ultimately have it memorized, but let's say you only knew the one for sine. And you're thinking, okay, I know the one for sine. What could I do to sine to make it be cosine? And what's the answer? Well, I claim that cosine of x is equal to, and what could you do, calculus students, to sine of x to make it be cosine? That's right, you could take the derivative with respect to x of sine. So according to this expression, that would be exactly the same as taking the derivative with respect to x of the polynomial here. Or I should say the series that's equivalent to sine. Come on, that's adorable. So at this point then, what would we know? We would know that the cosine of x is exactly the same as just taking the derivative of this polynomial. So what's d dx of x? 1. d dx of x cubed over 3 factorial. So you'd have essentially 3x squared over 3 factorial, but the 3's cancel. So what are you left with? Derivative of x to the 5th over 5 factorial. And the derivative of x to the 7th over 7 factorial. Etc. And there are a couple takeaways that I'd like for you to have from this problem right here. One, you can seriously take derivatives of both sides of your equation, which you've known forever, but sometimes it surprises people when you have something that's infinite, but that's a thing. And then in addition to that, now you have the Maclaurin series for cosine of x, and that is your second to last flashcard of your collection. And how are you ever going to memorize such a thing? Well, sine had all odd powers and all odd factorials. Cosine, remember that was an even function, and it has all even powers and all even factorials. Some people look at the 1 and they say, well, I don't see the odd power there. Well, 1 is the same as 1 times x to the 0, and you're also dividing by 0 factorial technically there. So you do have all even powers, all even factorials. Notice cosine also gets started off on a positive term, so you could use those patterns to have that memorized. Okay, so I think we'll do this lesson in 2 pieces. Because I'm pretty sure my son is going to need my attention pretty soon. So let's look at, let's give you the very last flashcard here. Then before we do the next part of the lesson, let's have you memorize these 3 so that you'll feel nice and prepared for the next thing. So the last flashcard is showing the polynomial expansion for e to the x. And that is the very first example that we ever did back in section 8.7. And remember, all the derivatives of e to the x were e to the x. So I'll just kind of show you what your work might look like for that one. Let's see, here we go. So your work is probably going to look like this. This is back in section 8.7, and we were doing f of x equals e to the x. We did all the polynomials, and then this was the 4th degree Taylor polynomial of e to the x. And I'm going to write exactly this, just using factorials for the denominator. So I'll write 2 factorial here, 3 factorial here, and the 24 is 4 factorial. So e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on. And again, so that you feel ready for the next lesson, let's have you memorize these 3. You'll feel much better about your progress, I think, if you have the 3 Maclaurin series flashcards for this lesson nice and memorized. So that's sine of x, cosine of x, and e to the x. We'll see you in the next video.